Okay, so this time I'd like to just look into a very simple example here. So let's say we have x is a Gaussian distributed random variable with unit variance. So and with some mean mu there. So therefore the PDF is given by this guy here. I can expand this PDF into this form to match with the canonical form for the exponential family. And recall that like for exponential family, the canonical form is something like hx exponential eta transpose tx minus a eta. So therefore, as you can see just from by inspection, like the a eta is just mu squared over 2, and the sufficient statistic tx here is just x, and eta is simply mean mu here. So therefore we can let's say write the since mu is just eta here, I guess it's better to write everything in terms of eta. So we have the PDF now is px given eta, and with the canonical form like this. And from last time, we know that we can immediately write down the conjugate prior given the canonical form of the exponential family. So the conjugate prior will be something like h tilde eta exponential lambda 1 transpose eta minus lambda 2 eta and plus minus a tilde eta, something like that. Sorry, a tilde lambda. So this does not depend on eta. So something like this. Oh, I missed a 1/2 here. It doesn't matter, I guess. Oh no, I didn't. But I can substitute. Yeah, this is correct. But then like a eta is equal to that. Then I substitute into that. So therefore I have this here. And of course I have freedom of choosing like what is a eta here. Sorry, a tilde here, and also h tilde here. So let's say I just assume h tilde is a constant, does not depend on eta. So then if you look at this here, it's basically just another Gaussian distribution in terms of eta, right? So the PDF, this is just a PDF of eta when eta is Gaussian distributed. And by computing square, I can find out the mean and variance of this distribution of eta. So as you can see, like this is basically just minus lambda over 2 eta minus lambda 1 over lambda 2 square, something like that. As you can see, if I expand this guy here, I will have like eta square minus 2 lambda 1 over lambda 2 eta plus lambda 1 square lambda 2 square. The last term I don't really care because it doesn't depend on eta, but for the first two terms, if I multiply by lambda 2 over 2, this will give me back this term here, right? And this, I get lambda 2 and 2 got cancelled, is just lambda 1 eta coming back is exactly this term. So everything is good. So therefore, like, I know the mean on the variance of this distribution is actually, the mean is just lambda 1 over lambda 2, and the variance is actually 1 over lambda 2. So that's okay. And I can write down the PDF right away, p eta given lambda, as this, because for Gaussian it's really nice that as long as we know the mean and the variance, we know the normalization factor right away. That's just basically 1 over 2 pi multiplied by the variance. and of course I need to take square root for that. So therefore we have the, as we already mentioned, the mean of eta is just lambda 1 over lambda 2, variance of eta is 1 over lambda 2, and we can substitute back and get like what's lambda 1 and lambda 2 in terms of mu eta and the variance of eta, sigma eta square. So therefore, like with what's the PDF of the conjugate prior as written down, we can have the Bayesian update with some observations readily. So let's say if I have like n observation of the sufficient statistics, of course the sufficient statistics in this case is just itself, it's just equal to x. So let's say I have observed like nxi here. So remember that the update for the parameter lambda, lambda 1 and lambda 2 will be just lambda 1 updated by summing over all the sufficient statistics, and lambda 2 will be summing over the numbers of sufficient statistics n. So therefore I have, and of course I can go back and eliminate lambda 1 and lambda 2 and just look at like how mu n and sigma n squared is updated. So as you can say, mu n will be updated by this expression here eventually if I eliminate all the lambda 1 and lambda 2 here, and the variance will be updated by this here. So as you can see, if I have lots of observations, so basically n is big, then the sum of xi here and also n here is big, so therefore these two terms become negligible. Then the approximate will be just the average of the observations. That makes complete sense. Basically that's what you expect. If I want to estimate the mean, is basically just the sum of all the observations there, and also the variance in that case of the our final estimate is just equal to 1 over n. And again, it's very annoying for Siri. So so here like I just have a simple demo here. So I have let's say the true distribution has the mean 4 here, and again it's a unit Gaussian distribution, right? So you Gaussian distribute the random variable, right? So I basically pick around this 4, but it's not exactly equal to 4. Let's say like for example the first observation I have is here, 2 point something I guess, and let's say the original prior, I forgot what I put in, but the mean is a bit off, and the original hyperprior for the lambda is I think it's 1 and 1 I put in. But anyway, this is after one observation I update my lambda, so my new estimated distribution for the mean is like this. So if I have more observations, then things will get better. So let's say I have here, I just actually already 4 observations here, and I get closer and closer to the true mean, and eventually we'll get reasonably close. But unless you have infinite observations, we will forget to be exact, because what we observe is also like oscillating around the true mean 4 there. Okay, that's basically what I like to talk about this time. So thank you for listening.